this talk will be me and Taoning. Taoning is going to talk about some of the new tools he's worked on towards the end, and I'll give the starting part. Missing a little bit off the top. So this year, the minor fixes and enhancements is the smaller part of the talk. Most of the changes are pretty major, so it's going to be a little longer than normal. So among the minor enhancements, added a PCOMB option to support floating point output, and it also supports floating point matrix input, which is convenient if you've ever used PCOMB and wanted to use for something more mathy, or you can't deal with the 1%, tolerance on the RGBE format. This is a great way around that problem. I improved the ambient super sampling algorithm over the years. This has caused some problems with bias and even visible artifacts. So I worked a little bit on spreading the error around from the initial set of rays to find where we really need to add more samples. A new type has been added to the R-Flux matrix set of hemisphere subdivisions, and this is specifically for the CIE sky scanner pattern. There's a standard sky scanner pattern, which I learned about only a few years ago when people were saying, why is my Tregenza patches all wrong? And it's because it just has a different winding and a different starting 5 point than the Tregenza. Otherwise, it's the same. So we just added this capability. I did some optimization in the dot. I'm going to grab some water. Hang on. Did some optimization in the Tau language. That's valuable for large arrays. The select call, function call, is used sometimes to index very large arrays, and it was just doing a linked list to all the arguments and having to go down the full linked list to get to any one of the arguments. So this is a faster implementation that avoids the list. And I made RLAM and RSplit handle any number of file inputs. I found when developing the hyperspectral stuff that I needed to use RSplit to output to over 1,000 files, and I think the limit was 512, and rather than just bumping up the limit to some large number, I allocate, which I should have been doing in the first place. And then there was a bug fix recently in the distant light sort sampling that was introduced way back in 5.4. This was pointed out by Mike Pompeo of Light Stanza, where this test that they had was generating some noise that shouldn't be there, caused by penumbras that shouldn't have been there from the sun. So that was embarrassing and a late fix. So if you see problems with your sun calculation using -DJ option for jittering the light source samples, that's probably it. So now into I think we have 3 of these slides of major additions. The main thing that I worked on in the fall, after getting laid off from Dolby, thank you, Dolby, was hyperspectral rendering and the associated scene primitives. So this is an idea that I had years ago, but never implemented as a way around the limitation of the Radiance scene description language. Radiance itself is not that hard to add components, but then you have to add the components to all the materials, and then that breaks everything. So rather than modifying the material definitions, we add some patterns that will have spectral specifications that then modify the materials, so carry the spectra over that way. So there are 4 new types, or 5 new types for primitives that use spectral data in one form or another. There's the spectrum, spec file, spec func, spec data, and spec pict. And they do more or less what you would expect, and I'll explain further in the slides following. Simultaneously updated the ambient file format to support hyperspectral cache values. That was needed to get all that into the interreflection calculation, of course. But unfortunately, at this point, it's not in the photon map, and we are looking for funding to do that, which I'll discuss on the final tomorrow. So the rendering tools have new -CW and -CS options. There's also a -CO option, which I'll mention later, for controlling the spectral sampling. If you don't set any of these options, it just defaults to an RGB calculation and will reduce whatever spectra you give it to RGB. Right. So the -CW specifies the wavelength range, and that's what makes it hyperspectral, is you can go outside of the visible spectrum. And the -CS, that's how many samples. So with those two options, you can change what is going to happen during rendering. And then for the output part, RPIC supports not only RGB space, but XYZ to cover the full visible gamut, or you can specify your own color primaries for output with the -PC option. So in the case of RPIC, at least, it will do this full spectral calculation, when it runs, but then the output's got to be RGB or tri-stimulus of one kind or another. Not true of RTrace. RTrace can output full spectral and has other options as well, which I'll mention later. The -CO option, well, I'm mentioning it now, flag supports full spectral output in RTrace, and that's also supported by RFlux matrix and RContrib and RTPict. So RTPict can actually produce full spectral pictures. And then for single channel output in RTrace, you can specify photopic, scotopic, or melanopic luminance. So the output from our RTPict with the -CO plus is a hyperspectral picture format, which we're using the HSR suffix for, which extends the common exponent of RGBE to up to 24 in the default configuration, up to 24 channels. This is supported by the rendering tools and also pfilt, so you can use pfilt to filter and so on. Our crop to crop, our matrix ops, and the new RCOM tool, which I'll discuss. It's also supported by the RCode to BMP and RadCompare tools, which will ingest and compare. MakeLoom, Randomove, and MakeSource, which are little known and probably rendering tools and Radiance for animations, and well, MakeLoom is better known. We'll do all the calculations in spectral, but the ultimate results are RGB. And then, yeah, we'll discuss later others. So, and then finally, Taoning's going to discuss the new support for spectral skies that he's added with the full atmospheric model, Gen S Sky for generating spectral skies, and Gen S Day Matrix for generating spectral sky matrices for the year for annual simulations. And the new -A option, the EPWEA, supports that, outputting the aerosol values that are needed by the Gen S Day Matrix. Final page, but we're going to go into depth later. I've been working on a new C++ RTrace simulation manager class that I discussed last year. This has been put into the RxTrace tool, which sort of does the same thing RTrace does, and really is for demonstration more than anything else. But this year I've finished working on, or at least the initial version of the RPict simulation manager class and RxPict tool, which actually adds some functionality, including hyperspectral output and native multiprocessing. There might be an RxPiece tool coming out soon, as soon as I get around to it, because the class also supports tiled rendering. I'm thinking of a more general rework of the rendering process, like a super RContrib, but I have not gotten very far on that. So, more details on the hyperspectral rendering. And if you have any questions, just shoot up your hand. At any point, I'm happy to interrupt. The wavelength is partitioned into n equal divisions. It has to be between 3 and 24, which is modifiable at compile time with the max CSAMP macro. There's a reason this has to be a constant, and it has to do with the way the array structure is set up and passed around, and stack memory means setting it to something very large doesn't really work or make sense. But if you need it, you can do it. I did a bunch of tests myself with 81 samples. It runs fine. The input sample ranges and steps are converted during rendering. So whatever input you give it, it will convert it to the spectral sampling that you've told it to use. There are 5 new primitives, as I mentioned. Spectrum is a basic spectral color. It's just an inline color, inline spectrum. Spec file takes the same from a static data file. Spec func is programmable, similar to color func or something. Spec data, similar to color data, has a function as well as a data file. And spec pict maps a hyperspectral picture into the scene. So the updated ambient file format supports N hyperspectral samples as well as standard RGB, and it converts. So if you did a rendering with 12 samples and then you go later on and you reuse the ambient file for 18 samples, it will resample those 12 into 18 with some loss. So the caveat will give you a warning about that. So how does this work in practice? Well, we end up partitioning the spectrum so the interaction between RGB and spectra is well defined. So we partition over the visible spectrum from 380 to 480 nanometers for blue, 480 to 588 nanometers for green, and 588 to 780 nanometers for red. Those are the default intervals for those 3 channels. The green one will never change, but if you extend the spectral range into ultraviolet or infrared, that will extend the blue or red, respectively, to include those wavelengths. And the reason for that is if you have an RGB multiplier in your material that's not, red, green, blue, all the same, what do you do with that? Well, you use this partitioning to modify the wavelengths that those channels cover, basically. It's just a way that you can get some ability to manipulate the spectrum from the standard material. And there has to be an interaction defined between those anyway. The reason for those spectral ranges, as I discussed in the tutorial yesterday, is they were tuned to match the standard RGB of Radiance. So Radiance has a standard RGB set of primary chromaticities. If you integrate these over using a uniform spectrum, you get those color primaries back almost exactly. Any questions on this part? This is kind of the key part. It's still not sRGB. The green channel has a slight difference from sRGB. Yeah, unfortunately, Radiance sort of predates sRGB. Yeah, and I used the recommended monitor chromaticities Gary Meyer recommended, and I think sRGB ended up looking at those and saying, we'll just tweak them a little bit. Yeah, that's why we got where we are.
I realize that it may not be up, but there are Radiance challenges today, the material and lighting is maybe
No, it all plays well together. That's what I was saying, is it gets converted during rendering from whatever you specified to the rendering colors. So yeah. Obviously, you're going to have some loss if you don't do it right. But also, Malika, I should mention that the new -PC option, Malika, the new -PC option allows you to specify the output color space. So if you do the rendering in full spectral and you want sRGB output, you specify the sRGB primaries with the -PC, and it will do a perfect job of that. Oh, with the what? Oh, good question. Good detailed question. In most places, there's a new intensity call that checks for the maximum spectral value over whatever range you're rendering under and uses that to determine ray limits and things like that. That's if you're deciding when to truncate a tree. If you're needing a luminance value for some reason, then it usually, if it's in a critical part of the code, it will use an approximation that pulls 3 sample wavelengths that correspond to the central range of each of the primaries. But there's the more expensive calculation is to do the full, multiplication against the CIE standard observers and convert to from XYZ to whatever color space you need. Or to get photopic, you'd use the photopic curve. And there's code in there that does that for the critical parts, but there aren't that many parts during rendering that are that critical. I haven't tried that. That's actually a good question. It should be able to handle that case, but I'm not sure it does because it expects you to cover the visible spectrum. It will allow you to crop in a little bit from the ends if you want to, up to a certain point, up to where you're getting towards the center of the blue or red channels, then it will complain. And it will fail, I think, if you chop off too much. So probably just exits with an error in that case. I mean, if we really are serious about handling that case, we'll have to look more closely at how to do that. Because right now it's using this assumption of an anchored green. Good question. So now into the actual primitives themselves. Here's an example. To Rob's point, we have way more spectral samples than we can even render with the standard configuration. It gets reduced to however many samples you've said you're rendering with. So the default will be to reduce that to RGB. But if you say render it with 20 samples, which is often used, it will re-sample it into 20 channels. So I use the mouse. So this is a pattern that operates as a pattern in the Radiance parlance. Has 82 floating point values. The first 2 are the spectral range, and it can be given in either order. If you reverse the order, then you're starting from the longest wavelength and going to the shortest. In this order, I'm going from the shortest wavelength and moving to the longest. It's whatever order you say it's in. And it's always uniform steps. So that first value is actually not the value for 380 nanometers. It's the value that's halfway between 380 nanometers and the next step. So these are interval measures. I think, just to be clear. And then that pattern gets applied to a material or another pattern or mixed func or whatever you have in your chain. But in this case, we're just applying it to a metal which has perfect specularity and 111 for RGB. That means just don't change what I gave you. And these are absolute reflectances. But these can be anything, and these multipliers can be anything. So in the case of the sun, oftentimes this will be a standard solar spectrum, and then this will be the actual magnitude of the radiance value for the sun. The spec file primitive is just the same as the spectrum primitive, but instead of inline, it's in a file. This is very handy because you can have a list of spectra in your library and you just refer to them here, and we'll grab them out. So this is what the spectral file looks like. It's one-dimensional, specifies the spectral range and the number of samples, and that all works. There is a difference in this case. I think that I have to check my code, but I think that maybe in this case it's not the same because that first one might be centered at 380. I'll have to look. It depends on how I wrote the interpolate. The spec funct primitive allows you to specify an expression or a cal file that gives you the behavior you want. I think you have to give it the starting and ending wavelength, and I think this is just another argument that's used by the cal file. So yeah, A3 is actually a coordinate in the space. Confusingly, it's a dimensional coordinate. This is just a simple way to get a rainbow pattern on a wall. It's a little bit hard to explain, but there's a sampling process that goes on that's random, that randomly samples the spectral range you tell it, so that it doesn't give severe, quantization artifacts. And then spec data has not only the ability to have cal files or expressions, but it also has a data file, which can be anything. It has to be at least two-dimensional to make any sense, because the final dimension is the spectrum. So this is a blend between copper and gold. It has two dimensions, and the first dimension is just either copper or gold. And the second dimension is the spectral range and number of samples. And then that allows you to linearly interpolate between them. I'm using a cosine function to do that here. I'll show you the final image that puts these together. And this was done as part of the test suite, just so we test these new primitives. The spec pick primitive reads in this HSR file, the hyperspectral radiance file, and then otherwise is very similar to color pick. It has the main difference is the clip function. There's only one function instead of three functions that modify the data from this image, and they are have an additional parameter, which is the wavelength they're operating at. So if you have a function file that uses this, it can look at the second parameter and do something different based on wavelength. So this is the HSR file I gave it as input. And then the final rendering looks like this. There's the mapped HSR file in the scene. And then here we have the rainbow on the wall, which is the spec func. We have this mixture between copper and gold going on here. This is the gold spectrum. This is the copper spectrum. And this one is actually, I think, RGB gold. So it's an RGB version of that same gold. So you can see the difference between spectral and non-spectral. Yeah.
So grass the partition. So when you're putting your rainbow up, is it using like super widely? Well,
a good question. The banding is due to the way the colors are sampled and the way I've defined that particular material. It's just trying to select a band based on where the ray landed. And the size of that band, that dimension of that band, I think is the 45, like a 45 nanometer range that it's producing. So you can make that larger or smaller, and you get either more blending and less purity, or it was just a test. It's not meant to be, this is how you do a rainbow. It's sort of like, let's see what this does. What I just said. So the hyperspectral options are the -CW, as I mentioned, that the starting and ending wavelength, those can be in either order. It makes no difference. And the number of divisions, which can go up to 24 in the default compile. So example, you might do CW 300 to 800 with 10 steps. You get nice, no, I guess it doesn't show there's going to be division on there. And then there are color output options that specify what you get out. for RPIC and RTrace, you can do -PRGB or XYZ or -PC, as I mentioned. The RTrace, man, this got rescaled somehow when we have a different version of PowerPoint, probably. All right. Might be the fun. You can specify photopic, photopic, or melanopic luminance. And I don't know if anything went off the bottom of that slide. I can't tell. I had some point, but I can't read it now. Oh yeah, our contrib and our flex metrics all produce N channels. That's also true of our sensor, incidentally. And the new HSR pictures are produced by RTPIC, our flux matrix, and our contrib, and they can be manipulated, as I said, by pfelt, the new RCOM tool, RCrop, and our metric stop. And then the RCode to BMP script is really handy for visualizing any of the Radiance formats that are images. And rad compare also now understands them as well as that RCrop. The way this format works is the same as idea behind RGBE and our XYZE, but it just has more mantises. There is no run length compression. The header file also specifies the number of components and the wavelength splits. So the discussion around how those wavelengths get split, the endpoints get put into this header. So if you've specified a different range, that will change the 780 and the 380 to something else. You can technically move the 588 and 580 around as well, but it's not exposed to the user level. And then the format type is Radiance. I had some misgivings about extending this to Spectrum. I was afraid that the 8 bits was not going to be enough in some cases, and you would lose some accuracy if one wavelength had a very strong peak and it was overwhelming others. So I hedged my bets, and you can also output floating point matrices with most of it. Additional tool support comes from MGF to RAD. So MGF is natively spectral or has that capability, and the -S option of MGF to RAD will get you a conversion to Radiance descriptions. And then similar to, I mentioned our flex and our contrib, our sensor also produces the number of spectral samples you've specified. It's usually just reducing to a few values anyway, so it's not a big deal. I mentioned this already. The updated make Lumar, random move, and make source always produce RGB results. All right, handing over to Taoning, and I'm sorry for going long, but I'll stay up here for questions. Oh yeah.
So I'm going to give a more detailed presentation later in the afternoon. So here we're just going to go through the tools. So there is a new atmospheric scattering models that implemented in Radiance following the Brunette and the NARAD model developed in 2008 with modification to sort of increase its accuracy in terms of mostly the Mie scattering, which is the aerosol scattering. We sort of produce a set of pre-computed atmospheric scattering tables that we interpolate at around runtime. So the pre-computation is going to take some time, which I'll go into details later. So as a result, there are 2 command line programs, Gen A Sky, as S stands for spectral, and then Gen A state matrix, both for point-in-time simulation and annual simulation. So the Gen Spectral Sky produce a accurate rectangular hyperspectral sky map based on the atmospheric scattering pre-computed table. and then we can use that for a point-in-time rendering. And the GenS state matrix just directly samples a Braganza sky patch using the same pre-computed table. And then right now the input data to the Gen8 state matrix is not direct normal and diffuse horizontal, is broadband aerosol depth and cloud cover. So which we can discuss later. How do we improve that? So here is the options that we have for GenS Sky is intended to follow closely the patterns that we have for Gen Sky and Gen Daylit. The only difference is you can see there's a -n options for multi-threading. Because of the pre-computation that takes some time, we want to, so we implemented the multi-threading to help speed up the process. So this would work both on Linux and Windows natively. There are -d options to override the broadband aerosol optical depth. And there's C to give a total sky cover, and then L options that you can provide a custom mean scattering profile. So the default one we have is the OPAC continental average aerosol profile. You can generate a custom one if you want to generate a custom sky. And then -p options is where you store all the pre-computed table and then the hyperspectral image. And then the -f option is to give a custom name to your hyperspectral image. -g is ground reflectance, and then -r is the accurate rectangular hyperspectral sky map resolution. So you can increase this to have better gradients if you want to do that. So we added a -a option to the EPW to WEA that outputs the, in addition to the direct normal and diffuse horizontal, also the aerosol optical depth and then total sky cover. And then the results of that modified WEA file gets typed into Gen8 state matrix to generate a annual spectral sky following the same Tregenza/Reinhardt patch pattern. And then basically you have similar options that we have for Gen8 matrix. So this is just a few examples. I'll go into details later in the afternoon. So one of the benefits of having this atmospheric scattering model is that you can have a negative solar angle. So on the left is a solar angle of 15 degrees. On the right is a solar angle of -5 degrees. And then you can see there's a shadow band of the Earth showing up in the horizon there. So that's the shadow of the Earth with the sun below horizon. Yep.
So, yeah, please. They might have questions. Thanks, Taoning. So unfinished pieces, the photon map currently doesn't work with hyperspectral calculations. So if you set CS greater than 3, you should not be using the photon map. I actually don't know what it does. I just know that it works without the hyperspectral still. So Roland's going to have to look into that when we afford to hire him to do that. The current DC time step does not handle HSR input. Everything's built around 3 color channels, so it's not likely to be changing anytime soon. That means that annual simulations that are trying to generate images have to use other techniques, and I found that the new RCOM tool and RSplit work well together. Matrix multiplication with hyperspectral can be slow. That's why the RCOM tool has a -n option for multiprocessing. Still can be slow with large matrices. And then finally, the GenS Sky and GenS A matrix tools that Taoning just described only always use 20 samples, so and cover the default visible range, and that may change in the future. Also, we need to think about an calibration method. As you know, the weather tapes generally specify global and diffuse, and then the Perez model that you're using will try to hit those global and diffuse values. That's not the case with Jena SDA matrix or with Jena Sky. There's no options for saying this is the global and this is diffuse normalized to that. So we probably need to add some capability there, so it's not always trying to do an absolute calculation from perfect atmospheric data, because we expect the global and diffuse measurements to be a little more reliable. And I think that's it. So thanks. So if you have any other questions, are we way over? Stefan?
Yes. The only unreliability we found is the errors optical depth can be zeros. And in that case, we're just going to use the default one. I haven't found the column mismatch yet. Maybe I just didn't check enough EPW file. I see. Yeah, that's why. Yeah, that's why we wanted to have that calibration implemented.